So yesterday we were discussing about this Weiss theory of ferromagnetism, which as the postulate is like all the magnetic moment, they feel a molecular field of the order of gamma into m. So your m is your magnetization and gamma is the coefficient. And then all these materials they break up into tiny domains. So they do not have, initially they do not have a spontaneous magnetization, but the material is made up of many tiny domains where the domains are pointing in the opposite direction. And in that case, m will be equal to 0. But as you apply a field, so the domain walls, they move, and so depending on the field direction, the magnetization will be aligned along that. Now if you, let's say we plot, here we have m and we plot it against hm, the molecular field. So in the y-axis, x-axis I have the molecular field. So from the Langevins theory, so magnetization as a function of field will be at a constant temperature, which will be something like this, right? So it will be increasing with the magnetic field. As the field increases, magnetization increases. And now if we plot this equation now, so this is, let's say, another equation which we now introduced. So that will be a straight line, something like this. So this is a straight line, this equation. Okay, so this is a straight line with a slope 1 by gamma. So let's say this is our origin, this is point P. So now, so when we look at the graph, so we say, so P is a, so there are two possible solutions. So in graphical terms, so the equation, this has two possible solutions. So one solution would be when m is equal to 0, or whatever the value of m at this point P. So this is the two possible solutions. So we will see that this m equal to 0 is not, so it is not a stable solution, it's an unstable solution. So how? So let's say we have zero magnetization, and for some reason this material is exposed to the Earth's magnetic field, and it gets a magnetization of, let's say, this value. So this is the magnetization due to the Earth's, or for any fluctuation or something happens, and the system has a magnetization m. So if the system has magnetization m, so it will produce a molecular field of this order, Hm, which is gamma m. So what will be the order of magnetic field? So it will be, this will be the magnetic field, point P. So now, if the magnetic field is B, this much, so what is the corresponding magnetization corresponding to that value? So you will have a magnetization somewhere at C. So now, immediately if the C is a magnetization, so you will have a molecular field due to that magnetization, which will be, the value will be of this point D. And now when you have a field of D, the corresponding magnetization will be E, and so on. So what you see is, like, once you have certain magnetization, due to this hypothesis, that this condition, that we have a molecular field, so immediately you will see this will go on and you will reach the point P. So this point P, where the magnetization will be stable. Okay, so due to this molecular field. And also if you do the reverse way, so if the magnetization is higher than a P value, somewhere here, so you will do the same thing and it will revert back to P. So it will come back to P. Okay, so this is how this solution, this magnetization P is actually the solution for this M versus Hn plot. Okay, so that means we will due to this molecular field, you will always have a spontaneous polarization. So you can call it MS, or so this is your spontaneous polarization. At point P. So this is what we are doing it at a constant temperature. So we are assuming that temperature is, so here temperature is constant. Now the question is, how does it vary when you have a temperature, when you introduce temperature? So we can use the same concept here, but elaborate a little bit, just based on the same thing. So we will go back to our Langevin function. So which tells us that our magnetization is of this form. Okay, and where K is equal to mu H by kBT. So now we don't have any external field H. So this H is actually our molecular field Hm. Okay, so this is our molecular the coefficient of this ratio A. And then similarly, this situation, so this is, let's say, one equation, and the second equation is also the same like before. Now, to understand what is the role of temperature, so we plot, or we can manage it in a, do a little bit of manipulation. So what we do is, we express Hm as a function of so what we can do is, this equation we can write down as mu naught mu Hm by kBT. So which we can write down again as mu Hm by kBT into M by M0 into M0. Sorry, so here we have, in place of Hm, I substitute as gamma M, and then I divide by M0 and multiply by M0. So what I will get is M by M0 will be equal to, so kBT divided by mu gamma M0 into A. So when I change the right hand side and left hand side, rearrange it, so this is what I will get. So I can say this is another equation. So now we solve. So we have one equation, this which is our Langevin function. So M by M naught is given by this, and another equation, due to the molecular field, we have something as a function of A. So now, so both are function of A. So to find a solution, so we do this graphical solution of this. Okay. So what we do is we plot the graph. So maybe I will write down these two. So one is M by M0 equal to what? Hyperbolic A minus 1 by A, and another is M by M naught equal to kBT by mu gamma M naught into A. So these are the two equations which we want to plot. So we have M by M naught in this axis and A in this axis. So the first one is again something like this. Okay. And the second one, so depending on the temperature, so we will have, so this is your basically your slope. So depending on the temperature, so let's say at a temperature, okay, sorry, so one temperature we call it T2, let's say, and as you increase the temperature, so this will rotate anti-clockwise. So it is, let's say, another T2 prime, and here at certain temperature, so it will be like just will be meeting at the origin 0, so we call it T3, and then maybe at a higher temperature. So this equation 2, this is how we can plot it. So what you see is, like, as you increase the temperature, so the slope is increasing, and then basically this straight line is rotating anti-clockwise. And so for this, at this temperature T2, you will have certain magnetization. As you decrease, so the magnetization, the saturation magnetization decreases. So this point, as we saw before, this point P, where we will have a spontaneous polarization, that value is decreasing. So as you change the slope with temperature, and then at certain point it is just like a tangent at the origin to this curve. So to the black curve, so this rate at T3, it is just like a tangent. So that means M is just will be 0 at that temperature. And we know that that temperature is a Curie temperature where magnetization goes to 0. Okay? So T3 will be our, so this temperature T3 will be actually our Curie temperature Tc, because at this point, so the slope here at the origin, so this is the solution is only we have at the origin, and we have a 0 magnetization at this temperature. So above this temperature, you have some finite spontaneous polarization. So this P value, so this is, let's say, P2, this is P2 prime, and so on. So the point, the value of spontaneous magnetization will be changing, and it will vanish at a temperature T3. So when the magnetization vanishes, that means that is our Curie temperature. And so we can also write down a relation between Curie temperature and these parameters. So what we can assume, let's say when we are close to the Curie temperature, so our value A, so A is basically our mu h m by kBt. So which will be less than or equal to 1. So in that case, we can assume that this m by m naught will be equal to, so in that case, m by m naught will be equal to a by 3. So that means the slope, so close to at Tc, so the slope, that is kBt, now we call Tc, mu naught gamma m naught will be equal to 1/3. So then you can have an expression for Tc in terms of these parameters. So it will be mu gamma m naught by 3k. This is an expression for Tc. Okay. So and what will be the slope at any other temperature? So the slope at any other temperature will be, we can just substitute here this kBtc term, we can rearrange using this equation, and in that case our expression will be M by M naught will be T by 3 Tc. Or the slope of this, so this slope, rather this one. So the slope will be, so Kb T by mu naught gamma m0, so will be T by Tc. So not this one. The slope will be this much. Yeah. Okay, so but typically when you do this, when we look at the temperature dependence, so one thing we assume that our uh, m by m naught, this m by m naught is a function of a, right? And we assumed, so m normally we write it like n mu, right? So n is our number of magnetic moments per unit volume. So one thing one has to be careful that this n, value of n, is not constant as you change temperature, right? So when you change temperature, this value might change because of thermal expansion. Okay, so then this density of magnetic moment can change, and therefore instead of taking m, so what one should take is something called Ng, which is number of magnetic moments per unit mass. So because this value will remain constant and doesn't matter, it will not change as a function of temperature, and in that case, so this equation m by m naught, instead of writing m by m naught, you can write it like sigma by sigma naught. Okay, so this is your basically KBT. So you can do the same exercise, just replace sigma by sigma naught instead of m by m naught. Yeah, sigma naught into A and so on. And this is your specific magnetization. We did that in the first few lectures. So this is your specific magnetization. So in that case, you do not worry about this value of n because it is not going to change due to thermal expansion. Okay? Yes.
Sir, we can't see bottom part of the water.
Okay. Okay, so I'll write down here. So what I told basically is, if you take this m by m0, this ratio, so m is defined by n into mu, right? So n is your number of magnetic moment per unit volume. But this value will change with temperature because of thermal expansion. Okay, so the volume does not remain the same. So since when you change the temperature, so there will be some expansion, and that will lead to a change in n. So instead of that, one should take this number of magnetic moments per unit mass. So that is going to remain constant, and then instead of m by m0, you replace it by sigma 0. So where sigma is your specific magnetization or mass magnetization also. That means this is magnetization per unit mass. So this is here the unit is EMU per centimeter cube. So here the unit is centimeter per gram. Okay, so this is what just the difference. Otherwise, you can do the same physics and only one in that case. So the molecular field will be gamma So it was gamma m. So you have to write it gamma rho by m by rho. So which is your gamma rho by sigma. Okay, so this is your coefficient. So not gamma but gamma into rho. Rho is your density. Okay, so this is the molecular field will be. So we'll complete this magnetic ferromagnetic part with so two more things I want to discuss on this ferromagnetism. So one is when we talk about this molecular field, I did not, or even Wiles did not explain what is the physical origin of this molecular field. So this HM, what is the physical origin of it? It was not known even until like 1920. So this theory was developed in 1906, but the physical reason why we have a molecular field is not clear. But one thing what you could understand from all this exercise is ferromagnetism is basically so if you take atoms, so you have paramagnet or diamagnet. But to have a ferromagnet, you need to have some kind of interaction between the magnetic moments. Okay. So when I put like a domain, so just take one domain, let's say, or let's say we assume everything in a single domain state. Okay. So all the magnetic moments are pointing in one direction. Okay. So that means I will have some kind of interaction between these magnetic moments, which leads to this parallel alignment or alignment along one particular direction. So if that is the otherwise you will not see the ferromagnetic material. So this is, you could say, this is a cooperative phenomenon, or there should be some interaction among magnetic moments. So what is the possible way that magnetic moments can interact? So the only way people thought of was like the dipolar interaction, right? So these are all like tiny dipoles. So you could say there will be some dipolar interaction. But in fact, when you calculate the energy due to the dipolar interaction, so if you assume an atomic magnetic moment, so mu of, let's say, you can assume, so just assume, let's say it is 1 mu volt or few mu volt, 2 mu volt, something like that. And then you calculate the dipolar energy. So you can consider that they are parallel or anti-parallel, like that. You can calculate the dipolar energy and you will see that this energy what comes out is very small, so it is not able to align the magnetic moment. So in terms of this energy, so you can write it as a units of kV and temperature. So it will be of the order of 10 Kelvin. Okay. So this energy which is responsible for the alignment of the magnetic moment will be of the order of, if you just assume dipole-dipole interaction, so this is of this order, 10 Kelvin. So that means the ordering can happen only up to few Kelvin, so very low temperature. So if you go to high temperature, so there will be no alignment basically. That means if the temperature is greater than 10 Kelvin, so the system will be paramagnetic. So based on what is, this is based on that the interaction is dipolar. So magnetic dipole, magnetic dipole-dipole interaction. So if you, so that point people actually said yes, dipolar interaction is not responsible for this molecular field. But later on, when quantum mechanics was developed, So we will not go into detail, but this is one fundamental equation which is associated with ferromagnetism. So it is known as the exchange interaction, Si dot Sj. Okay, so this is known as exchange interaction or exchange force, sometimes also called exchange force. So this is an energy term again, and this is Si and Sj are basically so Si is and Sj are spin angular momentum of the atom or the electron, or it can also be due to the molecule as well. So if I have two different moments, magnetic moments, so it's spin angular momentum Si and Sj, and they will interact in such a way. This is called exchange interaction, and that will lead to a ferromagnetic interaction or any magnetic interaction, and that will lead to so this exchange interaction leads to a long range ferromagnetic order. Okay. So this is purely like interaction between the spins of this nature. So we'll not go into the detail. Just I want to highlight that because you remember, or you, if you go into further in future, know about more about magnetism. So this is the fundamental interaction. So which is basically a spin electron spin interaction, and that can lead to ferromagnetism like parallel alignment or anti-parallel alignment. Okay.